Availability design is about keeping services running through failures and disruptions, not pretending those failures will never occur.
In real systems, hardware breaks, software crashes, networks partition, and human error intervenes at the worst possible moments.
Security architecture that ignores availability creates fragile systems that technically protect data but fail the business the moment something goes wrong.
Designing for availability means accepting failure as normal and planning for it explicitly, rather than treating outages as exceptional events.
When availability is designed in from the start, systems degrade predictably instead of catastrophically, and recovery becomes a controlled process rather than a crisis.
Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Fault tolerance describes the ability of a system to continue operating even when one or more components fail without requiring service interruption. In a fault-tolerant design, the failure of a disk, server, or network path does not immediately surface as downtime for users. This is typically achieved by having parallel components that can take over instantly, often without human intervention. Fault tolerance is not about preventing failure, but about absorbing it transparently. These designs tend to be more complex and more expensive, which is why fault tolerance is usually reserved for the most critical services. The key architectural insight is that fault tolerance shifts the problem from reactive recovery to proactive resilience.
Redundancy is the structural mechanism that makes fault tolerance and high availability possible by adding spare capacity through duplicate components or alternate paths. Redundancy can exist at many levels, including power supplies, network links, servers, storage systems, and even entire applications. The presence of redundancy alone does not guarantee resilience, because redundant components must be independent enough that a single failure does not affect all of them at once. True redundancy avoids shared dependencies, such as common power sources, shared configuration errors, or synchronized update failures. When redundancy is designed carefully, it creates options during failure, instead of simply duplicating risk. High availability focuses on minimizing downtime rather than eliminating failure entirely, often through clustering and rapid failover mechanisms. In high availability designs, components may fail visibly, but the system restores service quickly enough that impact is minimal. Clusters monitor the health of their members and automatically transfer workloads when a node becomes unavailable. Failover speed, detection accuracy, and state synchronization determine whether users experience a brief delay or a prolonged outage. High availability systems require careful tuning to avoid false failovers or oscillation, where the system thrashes between states. The architectural goal is predictable, fast recovery that users perceive as continuity rather than interruption. Single points of failure are the elements that can bring an entire system down if they fail, and identifying them is one of the most valuable exercises in availability design. These points may be obvious, such as a single database server, or subtle, such as a shared authentication service or configuration repository. Attackers also look for single points of failure because disrupting them can have disproportionate impact. Once identified, single points of failure become candidates for hardening, redundancy, or architectural redesign. Some single points cannot be eliminated entirely, but they can often be protected with additional monitoring, backup strategies, and recovery plans. Making these dependencies explicit reduces unpleasant surprises during incidents. Load balancing plays a dual role in both availability and scalability, by distributing requests across multiple instances of a service. From a resilience perspective, load balancers allow traffic to be shifted away from unhealthy components automatically.
They also enable rolling updates and maintenance by draining traffic from instances without taking the entire service offline.
Load balancing decisions influence failure behavior because poorly configured balancing can overload healthy components during partial outages. Effective designs include health checks, capacity awareness, and graceful handling of sudden demand spikes.
When load balancing is aligned with redundancy, it becomes a powerful tool for maintaining service continuity under stress.
Geographic redundancy extends availability beyond a single site by distributing systems across multiple physical locations or regions. This protects against site-level outages such as power failures, natural disasters, or major network disruptions. Geographic separation must be meaningful because co-locating redundant systems in the same risk zone undermines the benefit. These designs introduce additional complexity around data synchronization, latency, and operational coordination. They also require decisions about which regions are active, which are standby, and how traffic is routed during failures. When done well, geographic redundancy transforms regional disasters from existential threats into manageable incidents.
Data replication is central to resilient design, but replication strategies have significant implications for consistency, latency, and recovery behavior. Synchronous replication ensures that data is written to multiple locations before being acknowledged, which provides strong consistency but increases latency and couples failure domains. Asynchronous replication improves performance and decouples sites, but it introduces the possibility of data loss during sudden failures. The choice between these approaches reflects business priorities and risk tolerance. Architects must understand how replication affects recovery point expectations and user experience during failover. Data strategy is often where availability, performance, and correctness collide most directly. Quorum and consensus mechanisms are used to coordinate distributed systems and prevent conflicting decisions when components lose contact with one another. These mechanisms ensure that a majority agreement is required before certain actions proceed, which helps prevent split brain conditions where multiple nodes believe they are authoritative. Without quorum controls, distributed systems can diverge silently, leading to data corruption that is far worse than a clean outage. Consensus algorithms introduce overhead and complexity, but they provide strong guarantees about system state under partition. Understanding quorum behavior is essential for designing systems that fail safely rather than inconsistently.
Graceful degradation is the ability to maintain partial service when full capacity is unavailable, instead of failing completely. This may involve disabling non-essential features, reducing performance, or serving cached or read-only data. The goal is to preserve core functionality even when resources are constrained or components are unavailable. Graceful degradation requires deliberate design choices about which features are critical and which can be sacrificed temporarily. It also requires communication, so users understand that reduced functionality is intentional rather than a defect. Systems that degrade gracefully maintain trust during incidents instead of appearing broken or unpredictable.
Capacity planning supports availability by anticipating peak loads and preventing failures caused by resource exhaustion. Many outages occur not because components fail outright, but because systems become saturated and stop responding in a timely manner. Capacity planning involves understanding normal usage patterns, growth trends, and worst-case scenarios, such as sudden demand spikes or partial outages. It also includes maintaining sufficient headroom so that failover events do not overload remaining components. From a security perspective, capacity exhaustion can resemble denial of service conditions, whether accidental or malicious. Proactive capacity planning therefore supports both reliability and resilience against abuse.
Monitoring is the mechanism that detects early warning signals before failures escalate into outages.
Indicators such as increasing latency, rising error rates, queue backlogs, and resource saturation often appear well before total failure.
Effective monitoring provides actionable insight rather than raw data, allowing operators to intervene while there is still time to respond.
Monitoring also validates whether redundancy and failover mechanisms are functioning as intended during real events.
Without monitoring, availability design becomes theoretical because failures are discovered only after users are affected. Visibility turns resilience from an assumption into an observable property. Dependency mapping reveals how failures in one component can cascade into multi-service outages, often in unexpected ways. Modern systems rely on complex webs of internal and external dependencies, including identity services, messaging platforms, storage systems, and third-party integrations. A failure in one shared dependency can simultaneously disrupt many otherwise healthy services. Mapping these relationships allows architects to identify hidden single points of failure and prioritize mitigation. It also supports incident response by clarifying which services are likely to be affected by a given outage. Without dependency awareness, recovery efforts often chase symptoms rather than addressing root causes. Resilience requires deliberate design choices across infrastructure, data, and operations, rather than reliance on any single technique. Fault tolerance, redundancy, and high availability each address different aspects of failure and must be combined thoughtfully to produce reliable systems. Eliminating single points of failure, balancing load, replicating data, and planning for geographic disruption all contribute to continuity under stress. Operational practices like monitoring, capacity planning, and dependency mapping ensure that designs perform as expected in real conditions. When availability is treated as a first-class architectural concern, systems fail in controlled, recoverable ways rather than collapsing unpredictably. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.